Hello, my name is Jeremy Gibbons. Together with Sriram Krishnamurthy, I am Editor-in-Chief of the Journal of Functional Programming. This year we're trying out a new interaction between JFP and ICFP. Authors of JFP papers published in the previous year are offered the opportunity to present their work at that year's conference, provided that the paper hasn't arisen out of an earlier presentation. This year, authors of 8 papers took up the opportunity, and their presentations are collected in this session. Copies of those papers are freely accessible on the JFP website, with links from the ICFP website. The session is being streamed twice, once at a convenient time in New York, and again 11 hours later at a convenient time in Asia. I remind you that registered ICFP participants will get the full experience through Clouder, including text chat during the talk. Depending on the availability of the authors, there may also be a live video Q&A session after the talk in the New York stream, and I will announce that at the end of the talk. But there's no live Q&A in the Asia stream. The first talk is a presentation of the paper A Theory of RPC Calculi for Client-Server Model, which extends existing stateless calculi to cover stateful interactions. The authors of the paper are Kwanghoon Choi and Byeong-Mo Chang, and Kwanghoon will be presenting.
Hello everyone. I'd like to give a talk about a theory of RPC calculi for client-server model. My name is Kwanghoon Choi. This is a joint work with Byeong-Mo Chang. Let me start with the background. Developing distributed systems is known as complex and error-prone. For example, consider a web system. You have to develop 2 programs, one for client and the other for server, generally in 2 different form languages. Also, the 2 programs need to be put together for testing and maintenance. Tier-list program languages, also called multi-tier form languages, can address this problem. You have only to develop a single tier-list program. Assuming a client-server model, the slicing compiler will automatically slice it into a client program and a server program. The communication between the 2 sliced programs will be automatically supported. Particularly, we are interested in a seamlessly tier-list program language for client-server model. It is basically a program language designed for a single computer, but naturally extended with the seamless RPC. By the seamless remote procedure call RPC, I mean that the remote procedure calls are language supported, bidirectional, and fully transparent. Links is a real-world seamlessly tier-list program language for a client-server model. An advantage of the seamlessly tier-list program language is this. If you look at this example program written in links, you know that the tier-list program can be written exactly in the same way as writing single computer programs. The only difference is specifying the locational function. Here, client means that the main is a client function that must run at client. Here, server means that the authenticate is a server function that must run at server. Firstly, it is language supported, not library based. Second, you can call a server function from the client, and also you can call a client function from the server, so it is bidirectional. Third, the same syntax of Lambda application is used both for local procedure call and remote procedure call. No extra RPC keyword is used in the syntax. So, links is a seamlessly tier-list program language for client-server model. The RPC calculus is a seamlessly tier-list calculus that extends the Lambda calculus with an RPC feature. It was proposed as a foundation of links by Kufa and Wadler. In the calculus, C is the client location, S denotes the server location. every lambda abstraction has a location annotation A, meaning that this must run at the specified location A. The RPC feature is described by the big step semantics. When you evaluate a lambda application at location A, you evaluate the functional term L at the same location A into a lambda abstraction with location annotation B. You also evaluate an argument M to a value W at the same location. And then finally, you do beta reduction at the location B, not A. In the semantic rule for lambda application, the caller location A and the function location is B. If A is different from B, then the lambda application LM is a remote procedure call. If A is the same as B, it is a local procedure call. We use the same syntax for both calls, so it is fully transparent. The sim-list RPC is good for tier-list programming. However, due to the transparency of the sim-list RPC, every lambda abstraction has to check the function location in runtime to decide if it is an RPC or not. This happens even in the sliced client and server programs after the slicing compilation. Our solution is to have located function types to track function location statically. Then we can statically decide if given lambda application is a local procedure call or a remote procedure call. As a result, programmers can enjoy the advantage of the sim-list RPC in the tier-list programs, but no more runtime location checking is required in the sliced client and server programs. A key idea behind the typed RPC calculus is a location annotation on a function type. It is a reminiscent of a location annotation on a lambda abstraction. The located function type means that every lambda abstraction of this type is guaranteed to run at the specified location A. For example, the argument f has a client function type because a client function is going to be bound to f. In the second example, f has neither a client function type nor a server function type because depending on the value of if conditioner, both client function and server function can be bound to f. In the typed RPC calculus, only monomorphic locations are allowed, so it is not well typed. The other key idea is that in the typed RPC calculus, you can identify all remote procedure calls statically in compile time. Let us see its typing rule. This is a refinement of the conventional lambda application typing rule with respect to a caller location A and a function location B. Once your tier-list program is successfully type-checked, in every lambda application LM, the caller location A and the function location B are fully analyzed and known in compile time. When caller location A is equal to the function location B, then that lambda application is local procedure call. Otherwise, A is different from B, then this is a remote procedure call. In this way, you can statically decide if given lambda application is local or remote procedure calls. By the type soundness property, every remote procedure call thus analyzed statically will never be dynamically changed into any local one. Thanks to this property, we can design a location information directed slicing compilation whose sliced client and server programs will never do location checking dynamically in runtime. This is an advantage over the untyped RPC calculus that always does location checking in the sliced client and server programs. The typed RPC calculus is good so far, but it has a problem because of using only monomorphic locations such as client and server, not something to refer to both. For example, you cannot write a single polymorphically located map function. Instead, you have to write a client map function and a server map function separately. A solution is to introduce polymorphic locations to the typed RPC calculus. It is proposed by a sequel research to the JFP paper about a polymorphic RPC calculus. This is joint work with James Cheney, Simon Fowler, and Sam Lindley. In the polymorphic RPC calculus, you can write a polymorphically located function with location abstraction over location variable and location application as you see in the slide. Then you have only to apply it to the client location to get a client map function. You can also apply it to the server location to get a server map function. This slide shows a comparison among the RPC calculi. To support the slicing compilation of the polymorphic RPC calculus, there are two approaches. One is a static approach that is described in the sequel paper. The other is a dynamic approach that we are currently working on. In this talk, I presented a theory of RPC calculi. There are potential applications of location types to other areas such as security and communication optimization. Also, we wanted to develop a fully fledged seamless tier list functional form language based on the theory. Thank you for your attention.
Thanks, Kwanghoon. If you're watching the New York stream in Clouder, you should now see a Q&A link where I hope you can ask Kwanghoon questions by video chat. The next talk is a presentation of the paper The Full Reducing Krivine Abstract Machine KN Simulates Pure Normal Order Reduction in Lockstep, which adds to the framework for environment machines developed by Małgorzata Biernacka and Olivier Donvy. The authors of the paper are Álvaro García Perez and Pablo Nogueira, and Álvaro will be presenting.
In this talk, we prove properties of an abstract machine, in particular that the machine defines the same strategy than the normal order strategy of the lambda calculus. We prove this result by introducing a semantic artifact that corresponds to the machine, and that is better suited for the proof of the property. The corresponding artifact is a reduction strategy in a calculus of closures. As this quote by Krivine shows, the importance of full reduction is widely recognized in the theory and implementation of programming languages and proof assistants. Full reduction refers to reducing the term up to a normal form, that is, a term without any redexes. For instance, this is especially important with nowadays proof assistants with dependent types, which need to reach the normal form of a type in order to implement type conversion rules. The machine we study is Krivine's full reducing version of the Krivine abstract machine, which we abbreviate to KN. In a nutshell, KN takes as input a lambda term that it embeds in a closure with an environment that stores bindings, and uses a continuation stack and tracks the lambda nesting level of the term being evaluated. The machine looks up in the environment the binding of a variable represented by a De Bruijn index, pushes the operand of an application onto the stack, retrieves such an operand when the operator is an abstraction and places it as a binding in the environment, reduces the body of an unapplied abstraction by pushing a special symbol on the stack and placing in the environment the lambda nesting level of the formal parameter of the abstraction, calculates the De Bruijn index of such a formal parameter retrieved from the environment, reduces the operand of a normal form, which is embedded in a special kind of closure that stores pure terms, and finally flattens the stack into a normal form that is returned when all the symbols in the stack are consumed. KN has been proven to find the normal form of a term when it has some. However, the machine is a first-order transition system that manipulates environments and continuation stacks at the low level, and this format is not ready to deploy proofs by structural induction. Our approach is to introduce a higher-order calculus of closures with a reduction strategy that mimics the machine and that is suited for deploying proofs by structural induction, and later to prove that the said calculus realizes the normal order strategy of the pure lambda calculus. We arrive at such calculus of closures from the ones in the tradition of Krivine calculus of closures lambda rho. Krivine's calculus contains proper closures made up of a term and an environment. The term uses the De Broglie indices representation, the environment stores closures, and the indices are used to access the bindings in the environment, where positions in the environment start at 0. In the example here, reduction starts with a closure with empty environment. When an application is reached, its operand is embedded into a closure and prepended to the current environment. Then, the binding at position 0 is looked up and retrieved from the environment, and then reduction resumes on such binding. In the better rule of this calculus, the operator in an application is reduced in multiple step fashion to a weak head normal form. This poses some problems when defining a reduction relation which is purely single step. This issue was observed and fixed in Byeong-Mo Chang's lambda hat rho calculus. This variant of Krivine's calculus considers a constructor for closure application that enables the reduction relation to be lifted to the scope of the operator. The calculus also includes an expansion rule that expands applications to closure applications. This mechanism is reminiscent of the apply stage in the eval-apply evaluators in the classical literature in higher-order functional programming. Now, reduction expands applications, reduces the operator if needed, performs better reduction, and then continues to reduce as before. Byeong-Mo Chang's lambda hat rho is enough for weak reduction. They give account of both call by name and call by value weak reducing strategies in this calculus. However, it cannot accommodate full reducing strategies. We remedy this by further extending the calculus with a constructor for closure abstraction. We also provide a new expansion rule that expands abstractions into closure abstractions. But before presenting this rule in detail, we discuss how to represent the formal parameter of the abstraction in the environment. In our calculus, a variable is represented by a De Broglie index, which stands for the relative distance between the applied occurrence of the variable and its binding occurrence in the abstract syntax tree. If the binding lambda is immediately above the variable, then the index is 0. Otherwise, the index gets incremented as the distance to its binding lambda increases. However, if we place the De Broglie index of the formal parameter in a scope which is nested under more lambdas than its binding occurrence, then we have to adjust that index by adding to it the number of lambdas gone down. Inspired by Kn, we use instead the De Broglie level of the formal parameter, here overlined, which stands for the absolute lambda nesting level of the binding lambda in the abstract syntax tree. 1 stands for the first lambda, and the level increases if the binding lambda is farther down. The advantage of the De Broglie levels is that they need not be adjusted when placed in the scopes of the term that are nested under more lambdas. In order to use the De Broglie level, we first decorate our reduction relation with the current lambda nesting level, and then the expansion rule pushes into the environment the current level incremented by 1, since the formal parameter has crossed the lambda. We also add to the calculus a constructor for such levels, and we restrict the environments to either contain proper closures or levels, since this would be enough for the reduction strategy that mimics Kn. When a level is retrieved from the environment, the index corresponding to it can be calculated by subtracting the level from the current lambda nesting level. A new rule takes care of this calculation and embeds the calculated index into a new constructor for absolute indices. Absolute indices are formal parameters of an applied abstractions that are not relative to any environment. We show an example of a reduction sequence in our calculus. The sequence starts with a term with an empty environment and expands the application into a closure application. But now it also expands the operator to a closure abstraction before performing the beta step, which replaces the formal parameter by the operand. Then the sequence goes on as before. We also show how reduction acts on an unapplied abstraction. The abstraction is expanded to a closure abstraction, and later the level of the formal parameter is retrieved from the environment. Now reduction moves the scope to the body of the closure abstraction by the means of a compatibility rule that increments the level decoration of the reduction relation. Combined with the rule for index calculation, this results in the level 1 of the formal parameter being subtracted from the current lambda nesting level, which is embedded as the absolute index 0. Notice that the input term was already a normal form, and that reduction has only performed administrative steps which amount to flattening the explicit substitution in the closure into a term. Our main result is a one-to-one correspondence between the non-administrative steps in our calculus and the steps of normal order in lambda. This correspondence is captured by the commuting diagram here. On the top, 0 or more administrative steps followed by one beta step correspond to the one beta step on the bottom. A substitution function sigma mediates between the closures above and the terms below. The substitution function flattens a closure by performing only administrative reduction. The main technique used in the proof of this result is a structural induction on the derivation trees of reduction judgments, which has been possible thanks to the features of our calculus of closures. In a previous work, we used program transformation techniques to interderive Kn and the reduction strategy in our calculus. Together with this previous work, our main result entails that Kn and normal order perform the same beta reduction steps and in the same order. To conclude, our contribution has been possible thanks to the interderivation techniques and to a judicious use of scopes and levels in our calculus of closures. We have proven a result which is stronger than the known result that Kn finds the normal form of a term if it exists. Our contribution adds to the increasing corpus of knowledge on full reduction. We conjecture that variants of our calculus could be used to prove similar results for other full reducing strategies, in particular for the eager strategies in the call by value family.
Thanks, Álvaro. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Álvaro questions by video chat. The next talk is a presentation of the paper Local Algebraic Effect Theories, which extends the algebraic effects and handlers approach to track which equational theory the effects are required to satisfy in which subparts of a program. The authors of the paper are Žiga Lukšič and Matija Pretnar, and Žiga will be presenting.
Hi, I'm Žiga Lukšič, and I will present joint work with Matija Pretnar on local algebraic effect theories, which was developed to aid with reasoning in languages with effect handlers. When reasoning about programs, we often rely on certain equivalences, such as the ones stemming from mathematical properties. For instance, the functions f1 and f2 can be considered equal since x plus x is equal to 2 times x. Program equivalence gets much harder when we start using computational effects. For instance, when using print, it's not entirely clear whether printing the same string twice is the same as printing a doubled string. We do not know whether the language adds a new line separator at the end of each output, or perhaps the prints are counted for a message log. We must therefore know the specifics of the language implementation, so just imagine how much more difficult it becomes if effect behavior is user-defined. This is precisely the case in languages with algebraic effect handlers. In such a language, effects are modeled by operations which are assigned types in the so-called effect signature. For instance, here we have an operation choose that represents a binary choice. It accepts a unit argument and returns a Boolean value. The operation itself is only a construct, and its behavior is specified by the handler that intercepts the operation call. The choose_true handler has an effect case for choose, and here we have the unit argument of the operation call and the program continuation k, which is captured at the time of the operation call. The effect case states that whenever choose is invoked, the continuation is resumed with the value true. This causes every call of choose to simply return the value true. Now, when using this handler, the behavior is crystal clear. The code always returns 1 because choose always returns true. And for a slightly more interesting example, if we build a function choice that returns one of its two arguments, where the selection is again done by choose, we can again use the handler that always returns true, and in that case, choice always chooses the left argument, so the functions f1 and f2 are equal, since, well, they both always return 0. They're also equivalent in a broader sense. Every handler that results in an associative implementation of choice results in f1 being equivalent to f2. So another instance of a suitable handler is one that collects all possible results. And on the other hand, if we randomly select one of the options with a 50% chance, that is not a suitable implementation. The main issue here is how exactly to state such a property. One way to do that is to use equations. In the original approach to effect handlers, the theory consisted of an effect signature and equations between operations. For instance, associativity of choice, which is what we wanted in the previous example, can easily be expressed with an equation. Using equations allows us to abstract away from concrete implementations. We can focus on effect implementations that satisfy certain requirements that are set by the equational theory. The original approach assumed a single global effect theory, but this turned out to be very restricting. There are many useful handlers that work with entirely different theories, and by fixing a global theory, we're unable to use some of them. This is where our work comes in. We transition to local theories by packing equations into computation types instead. A computation type now states the type of return values, the names and types of operations that may be called, and the equational theory. At this type, all computations are considered equivalent modulo the equations E. Let's take a look at a small example. In this signature, we define an operation signal that accepts a unit and returns a unit. It really does nothing more than just signal to the handler that it was called. And in the effect theory, we can be a bit more expressive. The equation states that if we signal twice and then proceed with an arbitrary computation z, it's no different than if we signal only once and then continue with z. Now, an example of a handler that fits the equation is one that returns true as soon as a signal occurs and false if the computation is evaluated without a single signal. And an example of a handler that does not respect the equation would be a handler that instead returns the number of signals received. We can now use this equation to restrict possible effect implementations. Here we have two functions, f1 and f2, and f1 has no equations while f2 uses the above equation. This means that f1 can be handled by any handler for signal, while f2 requires the handler to not differentiate between one and many signals. We can, of course, use such handlers for f1 as well, but not vice versa. This already shows a difference between global and local theories, since in the global setting, we either require all handlers to respect the equation or none of them. In the first case, we can't use such a wide variety of handlers for handling F1, and in the second case, we can't use the equation as a reasoning tool in the body of the F2. And when implementing effect behavior with handlers, we of course need to be mindful of the effect theory that we're working in. The handler type informs us about the kind of computations that the handler is used for and what the resulting computation type is. Since two computation types are involved, equations occur in two spots. The E on the left sets the requirements for the implementation, and E prime on the right states the theory of the outgoing type. We have to check that for every equation in E, if we handle both sides, we end up with equivalent computations. The equivalence is considered in the theory of E prime, so we may be aided by the equations that are packed in E prime. Handler correctness is undecidable, so the proofs are constructed in a logic that is coupled with the type system. Using equations comes with extra work when typing handlers, but provides a strong tool for reasoning, and it's a very natural fit for algebraic effects. Local effect theories impose less restrictions than global ones, and we consider them an all-around improvement over global theories. Equations are vital for reasoning about effect behavior, and the type system can also be coupled with different kinds of logic, so we can use a system that fits the problem at hand. If we use local effect theories, the changes to the language are rather minor, and the resulting system is also easy to use. We do not need to switch to denotational semantics or to a full-fledged dependently typed setting. The drawback is clearly the need for user input when typing handlers, but handler definitions are the only point where this is required, so most of the work is still automated. Since the paper was published, we have done some considerable advancements. We have extended the language with recursion and some basic data types, just products or lists. We also included the non-trivial extension of subtyping, which greatly improves the usefulness of the language. All of this has been formalized in the Coq proof assistant alongside some smaller examples, and we also constructed a sound and adequate denotational semantics, which takes into account all the before mentioned extensions. The approach was also implemented on top of the F framework. We decided to use a bidirectional type inference as it's more suited for working with effect theories, but the system does not automate correctness proofs, which are left to the user. The proofs can be done by pen and paper, or they can also be constructed in the Coq formalization of the language. We also considered a few future goals. The important extension that has not yet been done is polymorphism. We wish to have types that are polymorphic in the value component, as well as polymorphic in the signature and equations. The extension could be far from trivial, but it's ultimately important if you want a language that can be used in practice. Another key aspect that we're not yet entirely satisfied with is proving handler correctness. Automation would be great, but even just easing the burden by providing better tools for user proofs would be a great start. Perhaps also very important is finding good use cases for local effect theories. We feel that we are now at a point where future work should be guided by shortcomings when trying to apply it to actual problems. Anyone interested is welcome to read our paper, and thank you for your time.
Thanks, Žiga. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Žiga questions by video chat. The next talk is a presentation of the functional Perl heterogeneous binary random access lists, which you can use, for example, to implement efficient typed environments for a well-typed interpreter. The paper is by Wouter Swierstra.
Thank you for that introduction, Jeremy. So my name is Wouter Swierstra, and I'm here to say a little bit about a functional Perl that I published in JFP last year. So let's start by talking about lists. So lists are one of the very first data types that we teach our undergraduates. And they're a great vehicle for explaining concepts such as higher order functions with maps and folds, recursion, or polymorphism. But as our students mature, they typically take one of two career paths if they're interested in functional programming. On the one hand, if they choose to go into industry, they quickly realize that if they need to store any serious amount of data, you need better data structures, such as finite maps or some form of balanced binary tree. Other students might pursue a career in academia, and in that case, they spend their time writing intrinsically typed evaluators for lambda calculi or any kind of fancy thing like that, which requires a list where the values stored in the list might actually have different types. And to do this in a type-safe fashion, you typically use something called a heterogeneous list, or H-list. So this paper asks the question, can we have our cake and eat it? Can we define a data structure that's both heterogeneous and efficient? And this isn't just a theoretical problem. So people who work in kind of industry and academia, such as David Christian and his co-authors at Galwa, they wrote an experience report on dependently typed Haskell in industry last year that they have this experience of profiling Crucible that showed that linear access imposed an unacceptable overhead on the simulator. As a result, they actually abandoned the type-safe dependently typed approach that they were taking in favor of data.map and unsafe coerce. So what's in the paper? So I show how to implement an heterogeneous binary random access list in ACTA. And this has the same API as just regular heterogeneous lists. So there's an empty structure, nil, and there's an operation to add new elements to the front of the list, and an operation to access elements within the list, a lookup or a bang bang. And all of these operations are both total and type safe. And furthermore, there are no coercions or lemmas necessary for everything to type check. It's intrinsically typed by design. So in this talk, I won't try to cover the whole paper, but instead I'll just focus on the homogeneous case, where we have binary random access lists originally proposed by Chris Okazaki in his book on purely functional data structures, and show how to implement that in AGDA in a kind of total and type-safe way. And then the heterogeneous version follows quite naturally from this. So if we need better than linear access times, we need to shift from lists to trees. And for the moment, let's just make the assumption that we only ever have to store 2 to the power n elements. And that's very easy to do because we can store 2 to the power of n elements in a perfectly balanced binary tree of depth n. So here are a few examples of such perfectly balanced binary trees where I'm going to draw black dots for the leaves storing data and white dots for the nodes which store no data. If I want to write this in AGDA, I can define a little data type for my trees indexed by a natural number corresponding to the depth of the tree. So I can have a leaf which stores an element of type A and has depth 0, or I can have a node which has 2 subtrees of equal length and then returns a tree which is 1 deeper. Now if I want to kind of denote any particular value in such a tree, I typically use a path through that tree. The data type path here is just isomorphic to a vector of Booleans, but it's nice to have this separate data type. And the idea is that this path tells me for every node whether I should go left or right. And then I can define a lookup operation which just follows that path through the tree, going to the left subtree if the path starts with the left constructor and the right subtree if it starts with the right constructor. At the end of the path, I know that I'll have hit a leaf and I can return the value stored there. And the important thing to notice here is that the type indices ensure that the depth of the tree and the length of the path coincide, so I can always return a value of type A. Now, if I only ever had to store 2 to the power n elements, this would be the end of the talk. But you'd be very right to complain that I can't just assume that everything is a power of 2. But there's one observation I can make, which is that any number can be written as a sum of powers of 2. Using its binary representation. And that's the key idea behind these binary random access lists. So a binary random access list consists of a list of perfectly balanced binary trees of increasing depth. And at the ith position in this list, there may or there may not be a perfect binary tree of depth I. So let's look at some examples. So if I need to store 3 elements in a binary random access list, I can do this with a leaf followed by a binary tree of depth 1. If I need 4 elements, I omit the first 2 trees, but I have a tree of depth 2. If I need 5 elements, I have a leaf, I have no tree at position 2, and I have a tree of depth 2 at the second position in the list. I guess if you're familiar with binary numbers, you can see how this works. So a number's representation in binary determines the shape of the binary random access list storing that many elements. So we'll need some binary numbers. Let's write that in EGDA. So we can have a simple type for binary numbers, which zeros and ones are the end of the binary word. And then we can define a successor operation which increments the binary number. The important thing here is that we have the least significant bit at the beginning of the binary number. So if we see a 0, we can flip it to 1. If we see a 1, we flip it to a 0 and recurse. So now we can finally kind of define our random access lists. And there are 3 type arguments that you can see here. A type A, corresponding to the type of the value stored in the random access list, the number n, which is the depth of the list as we're going down, and a binary number, which kind of represents the shape of the list, or the random access list, but it also kind of counts the number of elements in this list. So there are 3 constructors. So nil is the end of the list, and the kind of corresponds to the empty binary word. If we're kind of using a 1, if the binary number starts with a 1, we have a tree of depth n and a tail which kind of has the shape of the kind of binary, the remainder of the tail of the binary word. And if the binary word starts with a 0, then we have no tree, but we have kind of the tail of the random access list that we might still have. So the binary number counts the number of elements and determines the shape of our random access list. And one thing which you can see here is that the number n, it grows as we go down the list. And this is not what you might be familiar with if you're used to things like vectors, where the vector, the number kind of counts down to the end of the list. Here n counts up as we go down the list because there are kind of increasingly deeper trees as we go down the list. And typically we consider random access lists starting with n is 0, but it's good to be a little bit more general sometimes. So now we can define a data type for positions in a lookup function. And these positions, they kind of take a natural number and a binary number. And these positions they essentially combine the usual kind of linear position in a list and the path in a tree. So if we know that the binary number corresponding to the shape of the random access list that we're accessing starts with a 1, then we can choose to have a path of length n in the tree at the head of the list. That's what the here constructor does. The other 2 constructors there, they basically jump over any kind of tree which may or may not be there in the kind of outermost list-like structure until we find the tree that we're looking for, and then we have the path in that tree to one of the individual elements. And then we can define a lookup function in kind of quite a straightforward fashion now. If we want to add new elements to this is a little bit tricky. The first thing you might try would be to define a cons function, which takes an A, which takes a random access list, kind of starting with depth 0, and then kind of produces a new random access list where we have 1 more element. So we've kind of incremented the number of elements, which was represented by the binary number B. But if we try this, we get stuck quite quickly. As we kind of need to make a recursive call, the tail of the binary random access list actually has larger trees, and we're trying to add an A, which kind of no longer lines up somehow. So the solution is to define kind of a more general operation, a cons tree operation, which adds a tree of depth n to a random access list, starting with n, and then increments the number of elements stored. And then we have the degenerate case where kind of n equals 0 then corresponds to the cons operation that we have up there. But if you want to know a little bit more about that, the details are in the paper, but the cons tree operation closely mimics the kind of successor operation on binary numbers. So to wrap up a little bit, we can extend this to the heterogeneous case by writing a heterogeneous binary random access list indexed by a random access list which stores some type information for some universe U. And despite the apparent complexity, there's an example in the paper where I write an efficient lambda calculus evaluator using heterogeneous binary random access lists. And this turns out to be no harder than just using kind of heterogeneous lists as you would in a usual situation. Furthermore, it's fairly easy to port this code to Haskell. It turns out that you only need about 130 lines to define the data structure, the nil, the cons, and the lookup operations. Of which I should point out that maybe 10% is language extension pragmas, but there's nothing too fancy going on there. So in conclusion, if you can choose the right data structure, and one very nice thing about these binary random access lists is that there's no rotations involved, everything kind of stays in the same order, regardless of when we add things, that kind of stays well formed. And if we choose our type indices in such a way that we can enforce the key invariance that we're interested in, this ensures that all of our definitions can go through quite cleanly, and we really can have our cake and eat it.
Thanks, Wouter. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Wouter questions by video chat. The next talk is a presentation of the paper POPLMark Reloaded, Mechanizing Proofs by Logical Relations, which presents a new collection of benchmark problems in mechanizing the meta-theory of programming languages. The authors of the paper are Andreas Abel, Guillaume Allais, Alia Hamir, Brigitte Pientka, Alberto Mamiliano, Stephen Schaefer and Catherine Stark, and Brigitte will be presenting.
Hello and welcome. Thanks for coming. This talk is going to summarize our JFP paper, POPLMark Reloaded, Mechanizing Proofs by Logical Relations. My name is Brigitte Pientka, and this is joint work with Andreas Abel, Guillaume Allais, Alia Hamir, Alberto Mamiliano, Stephen Schaefer, and Catherine Stark. So today, mechanizations are commonplace in programming languages. However, they're also time-consuming, and there are few design guidelines. So what's the problem? The problem is that, in fact, proofs are tricky to write, both on paper as well as in proof assistance. There are a lot of challenging details to keep track of. On paper, it's hard to keep track of the dependency among different theorems and the definitions, and one might think that proof assistants are the answer. But in proof assistance, there's sort of another overhead we have to deal with. We have to build up an infrastructure for modeling, for example, bindings and contexts and so on. So there's quite a lot of time that gets into building this particular infrastructure. It's often hard to understand how different features interact. Difficulties increase with the size of the mechanization, and it can be really quite time consuming. You see this, that often a whole team of students is actually tackling some of these mechanization efforts. And experience very much matters. Now, the goal of this paper was to develop a benchmark problem that would allow us to gain a deeper understanding of the similarities and differences in how we mechanize problems in programming languages. Now, we as developers of proof assistants and libraries wanted to make our approaches more robust and identify primitives and abstractions to better structure proofs and bring down the cost of verification overall. So it's worthwhile to take a look back at POPLMark in 2005. Back in 2005, the POPLMark challenge was to mechanize system F sub. And this is a problem that can be fairly easily understood. It's described in types in programming languages. It can be mechanized in a couple of hours. It focuses really on representing and reasoning about structures with binders, in particular how we model the polymorphic function space. All proofs were syntactic by structural induction, and it was a great way of exploring different encoding techniques for representing bindings. In fact, people used strings, De Bruijn, nominal encodings, locally nameless, as well as higher abstract syntax. But on the flip side, it did not really identify any bugs or flaws in the existing system. It did not inspire the development of new theoretical foundations, nor did it push any of the existing systems to their limits. All systems were, in some sense, equally suitable. So we wanted to go beyond the POPLMark challenge, and in fact one doesn't need to go very far, one just needs to look in the conclusion of this paper and one sees that one of the problems and challenges the authors mention is proofs by logical relations. So our contribution here in this paper is to describe a tutorial for strong normalization proofs for well-typed terms using Kripke-style logical relations. There are really few standard textbook chapters out there that focus on strong normalization proofs. But although it has been really a gold standard in some sense to evaluate proof assistance using a strong normalization proof by logical relations. See, for example, Thorsten Altenkirs' work in 1993, where he used Lego to give a mechanization of a strong normalization proof for a simply type lambda calculus. Now, one difference between all this work and ours is that we are really focusing on well-typed term representations, and that leads us to a Kripke-style logical relation where we talk about extensions of typing contexts. And this also brings me to the challenges which really go beyond the original POPLMark challenge, because we need to model simultaneous substitutions and renamings, context extensions, structural properties such as weakening and exchange and strengthening play a much more central role. And in order to describe the reducibility definition, we need to have a way of distinguishing between inductive and stratified definitions. And last, we implemented our solution in 3 different proof assistants: Beluga, Coq, and ACTA. Now, I also want to mention some considerations that went into choosing this particular benchmarks, because there are, of course, many different kinds of logical relation proofs and Kripke-style logical relation proof. In particular, they've been very popular for reasoning about concurrent and imperative programs, where we reason about memory extensions rather than typing context extensions. Nevertheless, we focus here on logical relations proofs for typed terms, the simply type lambda calculus, no state, but we believe that this is a good springboard for richer theories, in particular dependent type theories. One problem in particular that often comes up when you think about dependent type theories is the notion of equality, and we need to sort of reason about soundness and completeness of algorithmic type-directed equality, and the proof of soundness and completeness of type-directed equality exhibits many of the same ideas and challenges that we have in the proof of strong normalization for simply type lambda calculus. And last, our guiding principle was really to design a benchmark that is reasonable, so a grad student should be able to do it after reading the tutorial. So how do we define strong normalization? So traditionally, we define it by saying M is strongly normalizing if all rewrite sequences starting in M end in a normal form. And this is often characterized using what is called an accessibility relation. But in fact, the proofs become increasingly annoying when we need to reason about all these different rewrite sequences and analyze different reducts. So an alternative was proposed by Femke van Raanstonk and Paula Severi, going back also to Gauguin, is kind of a modular approach to strong normalizing, where we have an inductive characterization of normal forms. And this leads to modular proofs, both on paper and mechanizations, and the proofs essentially become much simpler. So the first challenge problem is to prove the equivalence between the accessibility relation and the inductive definition of strong normalizing terms. And the second one is actually proving strong normalization for the simply type lambda calculus using that inductive definition. And that will have certain subproblems that we also then describe in the paper and outline the proofs. So in the remaining few minutes, I want to talk about our solutions. One, Beluga, which uses contextual higher abstract syntax, and then ACTA and Coq, where we used De Bruijn encodings. So Beluga is probably the youngest system among these 3 proof assistants. It supports higher abstract syntax based on the logical framework LF, and therefore it's of course great to model binding structures. Beluga also has built-in support for substitutions and renamings, and in that sense, it's kind of ideally suited for that particular problem. But it was also a great case study for finding bugs and make the system more robust. So in particular, it allowed us to find bugs in coverage checking and extend termination checking. And over the last year, we also implemented an interactive proof development mode, Harpoon, to make it easier to develop such proofs in general. But there is no proof automation. Now, Coq, on the other hand, we used the Brin encodings for modeling bindings. We had, in fact, two solutions developed by Katrin Stark and Stephen Schäfer. The first one was on well-scoped syntax, and the boilerplate code was generated by AutoSubs2. And the second solution focused on well-typed de Bruijn encodings, and the boilerplate was sort of proven manually. Both proofs were sort of very much developed in close collaboration with our proofs in Beluga, so they have a very similar structure. So everything can be proven as expected. It's maybe worthwhile noting that substitution and weakenings are functions mapping from positions to terms or positions to other positions. And repetitive proofs are then kind of factored out using proof scripts and coq tactics. It also led to a way of maybe rethinking autosubs. Maybe one should have an autosubs 3 where we actually can generate boilerplate code for well-typed syntax automatically. And last, ACTA, we used a generic syntax library from Guillaume Mallet. It worked very well for him as an expert user to test and stress test his library. It led, for example, to implementing additional generic results as part of the generic syntax library because they were missing. And the abstractions provided by the library led to very compact proofs. Now, the theory of renaming and substitution is, however, not internalized, and there's no automation. So overall, I think all of us felt it was a success. This benchmark did expose bugs and shortcomings in existing systems. It made libraries and systems more robust. It helped us restructure our proofs, and it helped us to gain a deeper understanding of each approach and how they're actually related. So benchmarks can be great. We would encourage you to explore them. Hopefully we'll see a solution from you. We already saw a solution developed in F*, which is wonderful. But we also hope that some of the considerations and discussions that led to the choice of our benchmark problem helps you to formulate other challenge problems. Of course, this isn't the end. So thanks for listening.
Thanks, Brigitte. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Brigitte questions by video chat. The next talk is a presentation of the paper Perturbation Confusion in Forward Automatic Differentiation of Higher Order Functions, which describes a long-standing bug in the implementations of these and two potential solutions. The authors of the paper are Alexander Manjuk, Barak Perlmutter, Alexei Radul, David Rush and Jeffrey Mark Siskind, and Barak will be presenting.
My name is Barak Perlmutter, and I'd like to tell you about a bug that we encountered in allowing derivatives of higher order functions. This work is part of a sustained effort to make automatic differentiation robust, performant, general, and ultimately ubiquitous, and of course correct. It should be as easy to take a derivative as it is to take a square root or write a loop. That means programmers should be able to take derivatives of anything whose derivative makes sense. So, derivatives of functions which themselves take or return functions, like solving an ODE or the derivative of map. And, of course, we want to take derivatives of functions which internally take derivatives, so we want to allow nesting. Let me set up what we need to explore this issue. I'll review our notation and terminology for forward automatic differentiation, although the same issue crops up in all other modes. We'll use forward for clarity. Then I'll talk about classic perturbation confusion and how it's avoided using tags. We'll think about derivatives of higher order functions and see how allowing them breaks the one-to-one correspondence between invoking derivative operators and taking derivatives, thus allowing this bug. After that's all unpacked, we'll look at ways to address the problem. In forward automatic differentiation, derivatives are piggybacked on primal values. So we have x plus x prime epsilon. X is the primal. X prime is the derivative value called a tangent. This is like a dual number. Like a complex number inside the computer, it's represented as a two-element pair. These are propagated according to the rules of calculus, and we have an operator for extracting the epsilon coefficient, the tangent of an output. I'll show how this is used to perform forward automatic differentiation on a simple but topical function. Let's say f of t is 1 over 1 plus e to the minus t. We define the operator d to take the derivative of f at a point x by feeding x plus epsilon into f, extracting the tangent of the output. We can take f of 2 to get 0.881. We can take the derivative of f at 2. We take f of 2 plus epsilon, crank that through. We get 0.881 plus 0.105 epsilon. We extract the tangent to get the derivative of 0.105. This function is also the solution to Verhulst's epidemic equation. The derivative is the rate of infection. So, did you really think you could go a whole talk without coronavirus? It used to be that nesting was a niche idea, but many applications demand nesting. When done in frameworks that don't support it, programmers end up going through all kinds of crazy hoops to get nesting working. Sed scripts to patch source code between multiple passes through preprocessors, manual closure conversion, all kinds of heroic technical debt-creating shenanigans. We want it to be natural. Here's some simple nesting. D takes a derivative at a point. On the left here is conventional mathematical notation for nested derivative. Notice how much nicer the functional notation on the right is. Regular calculus is better with lambda calculus, right? Look at the definition of D. Now there's this fresh thing that there wasn't before. That means we get a fresh epsilon every time we invoke D, so that nested invocations have different epsilon tags, and so their tangents don't collide. That's critical to getting the right answer. When I say epsilon I or a different tag, these might be implemented in lots of different ways, like by nested structures with existential types for safety or a variety of other techniques. We're abstracting all that away and just saying tag, different epsilon tags, different indices. Recent formulations often still get this wrong. For some of them, it's out of scope. You can't even express nesting. For others, they crash or get the wrong answer. The phrase higher order automatic differentiation is used in a bunch of different senses in the literature. When we use it here, we mean the hard one. This first definition, taking derivatives of higher order functions, not plain old higher order derivatives, and not derivatives of first order functions defined using higher order operators. What is meant by the derivative of a higher order function? Well, in part that was the motivation for the development of the whole field of differential geometry hundreds of years ago. But let's give a simple example, a binary curried function. So f of xy equals x squared plus blah blah blah. We can take f at the point 5 and get a function from y to 25 plus y cubed blah blah blah. We can take the derivative of f at 5, and we'll get the partial derivative of f with respect to its first argument. So a map from y to the derivative of that expression with respect to x at the point x equals 5 and y. I'm ignoring derivatives of functions whose domain is a function. Read the paper for that. In order for this to go through, we're going to have to extend the derivative operator. Well, not the derivative operator itself, whose definition remains the same, but its type, and also we have to extend the tangent operator. The tangent operator operates on numbers the same way, but on functions by postcomposition. Okay, now we're in a position to do something very disturbing, or quite amazing, depending on whether you like to build large correct artifacts or enjoy watching slow-motion train wrecks. So I'm going to define an offset operator S. It takes an offset u and a function f and returns f offset by u. Now I'm going to define d hat to be the derivative of s at the point 0. If we look at d of f at x, we expand things out, turn the crank, and we get f prime of x. Similarly, if we take d hat of f at x, we expand out the definition of d hat, turn the crank, and we get f prime of x. So we should have d hat equals d. But if we use them in a nested fashion, d is operating correctly on a scalar function h, takes a second derivative, but d hat gives us a constant function 0 when used in this nested fashion. What happened? Well, the fresh triggered when d was invoked, but the thing is ds of 0 returned a value which has a single tag in it, a single concrete tag. So when it's nested, we can get a collision. That's really bad. Okay, I'll unpack. That's the dirty laundry of higher order automatic differentiation. Now let's get to the bottom of this mess. What's the root cause? No, d was invoked once in the definition of d hat, but we can still get nested derivatives. And that's because derivatives of higher order functions breaks the one-to-one relationship between invoking a derivative operator and taking a derivative. It's like those corny jokes about engineers and accountants traveling with fewer tickets than people by hiding in the loo when the conductor comes to check tickets. There's a disconnect between allocating the tags and using the tags, and we have poor enforcement of the one tag per nested derivative calculation policy. The key issue is that we need to distinguish the tangents, the tags, for different derivatives, even though the different derivative operator is called only once. If we don't, we get perturbation confusion. Here's an idea for a workaround. We would have gotten the correct result if d hat had been left unreduced. So instead of writing that expression at the bottom where we use d hat twice, we could define d hat twice and use the two different definitions. That would be okay, except it's manual and horrible. We want programmers to just take derivatives and get the right answer and not have to worry about what's under the hood. So here's an idea for accomplishing this more transparently. We could use eta expansion. We would delay the fresh until all the arguments needed for post-composition of tangent are available, so it immediately beta reduces to a non-function containing value. So we'd have separate versions of d for scalar functions, binary curried functions, etc. This could also be accomplished using polymorphic recursion, although that gets hairy when the underlying language gets more complicated. Here's another idea. What's going wrong is that the value passed into the function whose tangent is being taken might have the same tag that's in play in that function. So we could augment it with a wrapper to guard the tag in the function so that if it occurs externally, the external one gets renamed away and then renamed back after being passed through. Okay, take-home message. We can import the standard definitions of derivatives of higher order functions into automatic differentiation, but allowing them breaks the automatic differentiation machinery. Now, it might be a stretch to call this the amazing bug. It's a pretty crowded field, but I hope you'll agree that it's an amazing bug. We have some ideas for solving this, and I propose two solution frameworks. One is based on eta expansion, and the other is on renaming tags away and then renaming them back when they're passing through the tangents of closures. Recent formulations of automatic differentiation still often get this wrong. For some it's out of scope, others get the wrong answer. The two solutions that I proposed, they solve the correctness issue, but they do have some issues with complexity. So we would like to work on this some more to get the efficiency right, both constant factor efficiency and these solutions, implemented naively at least, would seem to break some of the complexity guarantees that we'd like to make in automatic differentiation. Thank you for listening. I hope this story has been of interest, and I'd like to thank the organizers for arranging this fantastic virtual gathering under very difficult circumstances. I'd be happy to answer any questions.
Thanks, Barak. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Barak and Jeffrey questions by video chat. The next talk is a presentation of the paper Elastic Sheet-Defined Functions, Generalizing Spreadsheet Functions to Variable Size Input Arrays, which is about helping end-user spreadsheet programmers to write more flexible functions that work over inputs of arbitrary size. The authors of the paper are Matt McCutcheon, Judith Borchhaus, Andy Gordon, Simon Peyton-Jones, and Advait Sarkar, and Matt will be presenting.
Hi, I'm Matt McCutcheon, and I'm going to talk about a method of automatically generalizing spreadsheet functions to variable size input arrays, which we've nicknamed Elastic Sheet-Defined Functions. The spreadsheet is by far the most widely used functional programming environment because it's so easy to use, even for people unfamiliar with conventional programming. For instance, suppose we're shopping for a set of foods and the prices are given without tax. We want to compute the total amount we'll pay, including the tax. We just type our starting data into the cells and enter the formulas we want to calculate into other cells. If it's too mind-bending to calculate the tax on all the foods at once, we can do it for the apple and then copy the formula. We have to be a little careful with relative and absolute referencing, but if we make a mistake, it's easy to spot and fix. We can work one step at a time and always see all the data at once, so for a simple problem like this, we never have to think very hard. Now suppose we want to total a lot of shopping lists. Of course, rather than make many independent copies of the formulas, we'd like to reuse them so that if we have to fix a bug in the original formulas, the fix takes effect on all the shopping lists. Since we're familiar with calling built-in functions like sum, can we define our own function for the shopping list that we could call? In current mainstream spreadsheet tools we can, but we have to rewrite the logic in a separate programming language such as Visual Basic, which sacrifices all the usability advantages of spreadsheets. Fortunately, there's an easier approach that has appeared in many research systems, and we think it's only a matter of time before it becomes mainstream, the sheet-defined function, or SDF. To make our original formulas into an SDF, we just mark the cells that represent the inputs and output of the function and give it a name. Now we can call shop on the second list just like a built-in function. Semantically, the tool makes a temporary copy of the function body with our new input substituted in and returns the new output, though of course the tool can optimize this process. The user can open the temporary sheet to see what happened. This requires users to think a little harder, but we think many of them will be comfortable defining SDFs, and the rest will at least be comfortable calling them. However, we quickly run into a problem if we call shop on a shopping list of a different length than the original. When we try to put the pre-tax prices in the input range, they'll get cut off and we'll get the wrong answer. The result we'd like is as if the body of shop were resized to fit the input. How can we make shop behave this way? One approach is to let the entire array of prices be stored in a single cell. If we apply an operator like plus to two arrays, we're implicitly adding the corresponding elements. This will work regardless of the sizes of the arrays. This is a little more for users to learn, but it's a plausible solution for shop. However, for more complex SDFs, the array programming approach becomes unmanageable. Here's a sheet containing the transaction history for a bank account with interest compounded daily. To compute the balance after a transaction, first we apply the interest to the previous balance based on the number of days since the previous transaction. Then we add the amount of the current transaction. This example presents two new problems for the array programming approach. To line up the previous dates with the current dates, we need to shift the array in A4 down one element and add A3 at the top. Let's assume that a spreadsheet tool designed for array programming will have a shift down function to do that. But for the reference to the previous balance, if we tried to do the same thing, we'd end up with the whole array in C4 depending on itself, which won't work. To handle the iteration, we need to use a special function called vscan2 and pass a lambda function that computes each element from the previous one. Most users won't be able to come up with this unless they find an example on the web that's similar enough that they can adapt it to their problem. If that isn't bad enough, here's another SDF with a naive model of cascading delays in a bus transit system. The idea is that a departure from a station will be delayed if the bus that was supposed to make the trip hasn't arrived yet. We want this SDF to resize in three different ways: the number of time steps in the simulation in the vertical direction, and the numbers of stations and routes, both in the horizontal direction. There's mutual recursion among four of the arrays. While we think this is possible to write using array programming, it's going to be such a mess that I won't even try. So it seems we really do want to resize an SDF at the cell level, effectively generalizing it to handle inputs of variable size. We call the result an elastic SDF. Maybe the user could somehow specify how the resizing should work, but it turns out that for many SDFs, including all three we've seen so far, the user doesn't need to do anything because we can figure out the resizing automatically. That's the topic of our paper. Let's see how the generalization process works in the simpler shop example. For the purpose of describing our work, we use a textual notation for SDFs. Users don't need to know anything about this notation, though we have evidence that some users may find it helpful. Here we have the function name and the input and output ranges. Each line of the body describes a rectangular tile of one or more cells with the copied formula. For example, the first line describes these three cells. The given formula is placed in the top left cell and copied to the others with the usual adjustment of relative references. We can now write the elastic SDF that we want in this notation by introducing a length variable alpha that can take any non-negative integer value. Of course, if we set alpha to 3, we get the original shop back. We'll call this elastic SDF shop1 for reference in this talk, though the user would invoke it using the original name shop. When an elastic SDF is called, we set the length variables to match the argument sizes, in this case setting alpha to 6, and substitute them into the definition, giving an ordinary SDF that we can evaluate as before. Note that tiles may collide when they expand. We address this by labeling each reference with the tile or tiles it originally pointed to and having it read only from those tiles, even if others overlap them. Here, the reference in the sum reads the H7 of tile 4, while the output reference reads the H7 of tile 5. We do this for all SDFs, but to reduce clutter, we won't show the labels for the rest of the talk. The question immediately comes up, is the best generalization of a given SDF always clear? For one thing, we want a generalization that's well-defined, meaning that its references stay in bounds for all values of length variables. For example, if we set the height of the column H tile to alpha, but the height of the column G tile to 3, then when alpha increases, the H tile will be referring to undefined cells below the G tile, so this generalization is not well-defined. From now on, we'll consider only well-defined generalizations. To illustrate the next point, consider this contrived sum2 SDF that sums two arrays and adds the totals. Here are two well-defined generalizations. Sum2D allows the arrays to be different lengths alpha and beta, while Sum2S requires them to be the same length alpha. We say that Sum2D is more general than a Sum2S since it can be converted to Sum2S by substituting for the length variables. We prefer Sum2D to make sure we generalize as many degrees of freedom in the original SDF as possible. So given an SDF like SHOP, if there's a well-defined generalization that is more general than all the others, which we call principal, that's the one we want. Unfortunately, there are several problems that can cause there to be no principal generalization. We'll look at one of them. In addition to SHOP 1 that we saw earlier, SHOP has two other contrived but well-defined generalizations, one that uses only the first three items of the input and one that uses only the last three. None of these generalizations can be converted to any of the others by substituting for alpha, and since they can all give different answers on the same input, it should be intuitively clear there isn't a principal generalization that's more general than all three. The user probably wants SHOP 1, but we have to formalize that somehow. So we introduce the concept of a regular generalization, which satisfies several conditions on top of well-definedness, one of which is that a cell reference can't pick three elements out of a larger tile. So SHOP 1 is regular and the other two generalizations are not. Now, out of all the well-defined generalizations of an SDF, if we keep only the regular generalizations, we can prove that there's always a principal regular generalization, and that's the elastic SDF we use. This can be seen as the analog of the principal type of a term in a functional programming language. Our algorithm to find the principal regular generalization introduces all the variables it could possibly need, generates constraints on them based on the definition of regularity, and then solves the constraints. For example, because of the relative reference between the tiles in columns G and H, we generate a constraint that the heights of those tiles are equal. Again, this is analogous to a type inference algorithm in a functional programming language. We've seen that in order to have a principal generalization, we needed to introduce a concept of regularity that excludes some well-defined generalizations. We try to make it capture user intent, which inevitably involves judgment calls. Our goals, aside from having a principal regular generalization, are to support as many realistic SDF design patterns as we can, and keep the process predictable for users, even if they don't know the detailed rules. Our work represents the first draft of the definition. We expect that future work will refine it. This is all technically elegant, but we need to make sure we're actually making things easier for users. So we did a user study to compare elastic SDFs to the best existing alternative, namely array programming, on a set of tasks based on real-world spreadsheets we previously collected. I'd like to highlight a few findings. First, users experienced lower cognitive workload using elastic SDFs compared to array programming, based on a standard survey called the NASA Task Load Index. Second, we have partial data suggesting that users solve tasks faster on average using elastic SDFs compared to array programming. And finally, while users stated a preference for array programming for simple tasks, they preferred elastic SDFs for more complex tasks. This is no surprise given that complex tasks are much harder to solve with array programming. These results are really promising, though more work is needed to further optimize the user experience. So, we've seen briefly how we can use ideas from programming language theory to offer spreadsheet users an easier way to reuse logic on inputs of different sizes. You can find the full definitions, algorithms, and proofs in the paper. We look forward to making this functionality widely available to improve user productivity. Thanks for listening, and we look forward to your questions and feedback.
Thanks, Matt. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Matt questions by video chat. The next and final talk in this session is a presentation of the paper Emerging Languages, an Alternative Approach to Teaching Programming Languages by Saverio Perugini, which argues that a course on the principles of programming languages should not be structured according to those principles, but around emerging languages such as Lua and Alexia instead.
Hello, my name is Saverio Perugini, and today I'm going to be presenting our Journal of Functional Programming paper, Emerging Languages, an Alternative Approach to Teaching Programming Languages. I'm in the Department of Computer Science at the University of Dayton. So while the learning outcomes of a course in programming languages are well established, the most effective approach to teach a languages course is not a settled matter. There are a myriad of approaches. The two predominant approaches are the principle/concepts-based approach and the interpreter-based approach. There's also a paradigm survey-based approach. There are hybrids of these. Each involve challenges. In this work, we challenge the idea that a course intended to convey the concepts of languages should therefore be structured according to those concepts. We sought to teach programming languages from a different perspective. The approach we developed involves using emerging languages as a conduit through which students incidentally bump into the concepts of languages, the implementation options available for them, and the compelling consequences of those options on programming, which are the student learning outcomes, the SLOs of a course on programming languages. Now, when we say emerging languages, what we mean here is languages that have adopted functional features to some extent or another in the last 20 years or so. So languages like Lua, Elixir, Go, Python, and so on. And despite the moniker for this approach, the goal here is not to teach students emerging languages. And thus the course must not involve, or perhaps I should say devolve, into an isolated row investigation of a sequence of emerging languages. Rather, the goal here is to teach students the principles, concepts of languages as an intended, though unadvertised, side effect of covering these emerging languages under the guise of a survey course on a variety of hot new languages. The central thesis of this work is that this alternative approach results in a variety of course desiderata: scope for instructor customization, alignment with current trends in language evolution, practice, and research, and probably better aligned with industrial needs. What I'm going to discuss here is the rationale for, the course mechanics supporting, and the consequences of this approach. So the rationale for the emerging languages approach is based on some simple ideas. First, let's recognize that students think in terms of languages, not concepts. I call that the student language-centric perspective. Learning concepts of programming languages sounds dull and academic. Learning languages, especially new and emerging ones, and how those languages apply in domains in which students have passion, like game programming, Internet of Things, web frameworks, sounds like fun. So why not take advantage of the juxtaposition of these circumstances? If we tell students they're gonna learn Lua, Python, Ruby, that's something they can get excited about. Let's get students excited about what they're studying and then most effectively harness that motivating spirit to meet the learning outcomes of the course. Exploring the concepts, implementation options, and the implications of those options on programming. So step one, students think concepts, thinks languages, not concepts. Let's further recognize that students are motivated to learn emerging technologies they perceive as relevant to the software industry, even if they're only ephemerally relevant. That's what I would call the student relevance-centric perspective. Most average students are typically not going to get excited about a required concepts of programming languages course, whose description indicates the use of Lisp as an implementation language, which the students perceive as not being used in industry, not building the resume, and not helping them get a job. Students, however, are motivated to learn new hot languages and novel emerging technologies. Students perceive emerging languages like Python and Ruby as less academic, more fun, and more practically applicable to real-world problems than languages like Lisp, which they perceive as archaic and arcane. I think the reason for this perception is that this perception is formed and influenced by the culture of the online ecosystem in which students explore, probe, experiences new languages and new technologies on their own. Things like blogs, YouTube videos, Stack Overflow, GitHub, and so on. So why can't we teach students first class and higher order functions and closures in Python rather than Lisp? I mean, ultimately, nobody cares if a student can program Lisp. Rather, they care if a student can think like a Lisp programmer in higher order abstractions, metaprogramming, and a variety of other languages. So let's harness that process of programming language acculturation, incubation, in which students participate, perhaps unconsciously. Given those circumstances, we think it's reasonable to use emerging languages as a method or conduit by which to distill concepts of languages to students. And then, of course, let's build a course framework around that idea, and let's use course mechanics that leverage how students learn languages on their own to teach them concepts. So that's what we did. We designed a course framework to support that approach or to operationalize that approach. And the model we came up with involves it's a module-based approach. It involves 3 modules. It's a module-based design, I should say. It involves 3 modules. Students were given a foundation and a vocabulary in language, a brief foundation of vocabulary and language concepts through sort of a functional programming tutorial in module 1, which formed the background from which they deconstructed the emerging languages presented in module 2, deconstruct those languages into the concepts, and then probe those concepts for subsequent comparison, synthesis, use, application of those concepts in final culminating projects in module 3. So module 1, brief introduction, identification of language concepts. Module 2, deconstructing the emerging languages presented to probe those concepts. In module 3, reconstruct, synthesize, apply those concepts in projects. Now, that third module also helps connect those languages back to the concepts in module 1. Module 2 is really the heart and soul of the course. The most number of weeks, 6 to 8 weeks. It's really the body of the course, the meat of the course. Now, I do want to mention in module 2 is really where the instructor has the opportunity to emulate as much as possible the process by which students learn languages on their own through those online fora I was discussing earlier. So this is the module where we did YouTube videos, we did language cheat sheets or quick reference sheets, we did online style blog web pages, we did language synopses, a lot of active learning going on. Students presented each language over the course of 2 consecutive 75-minute periods, really trying to emulate the process by which students learn languages. This also provided graded preparation for their final, the same sort of mechanics that were used in their final culminating project. We've offered this course 3 offerings using this approach. And these are some of the languages that we used across some of those offerings. This is a subset of them. And this is the student artifacts and final projects and cheat sheets and YouTube videos are all posted in this GitHub site, which I probably will be able to demonstrate or at least illustrate later. Module 3 is really the module where students were given the opportunity to demonstrate a mastery of those concepts distilled during the emerging languages presentations. And really demonstrate how they can use their intuition to independently discern how and when and creatively harness an integration of a subset of those concepts that they absorbed in that module 2 to craft a solution to a practical computing problem in Module 3. The project involved a software system, formal term paper using the ACM conference style and LaTeX, and an in-class presentation to classmates. Now, without a formal research experiment, it's challenging to ascertain the merit of this approach in helping students understand the core language concepts. We can, however, offer some anecdotal and formal evidence. This table that I'm showing you here presents the observed frequency of the use of the language concepts in the source code of the final projects. Now, again, while the observation of an application and integration and a use of these concepts in the final projects cannot on its own serve as formal evidence that they understood the concepts, it does provide some anecdotal evidence, particularly because many of these projects were of high quality and some were even published. Okay, wrapping up here, what can you expect from this approach? What are the consequences? It's customizable. The instructor is picking different languages every semester. The mechanics are somewhat customizable, although to a lesser extent, because we're trying to use mechanics, which one of the main ideas here is using mechanics which dovetail nicely with how students learn languages on their own. It gets students away from their Java-centric worldview. We're covering a wide spectrum of languages in a relatively short period of time, which really radically shatters students' Java-centric worldview, promoting the idea that students should use languages for the particular problem domain. We're covering things like new concurrency models, CSP, Actor, Julia, scientific computing, Lua, game programming, MapReduce, so on. Promotes academic integrity. You're rotating the languages out every semester. Doesn't require a big, inordinate, and excessive work on the instructor's part because the students are producing the artifacts. Doesn't compromise learning outcomes. The outcomes are the same, the mechanism's different. Aligns well with industrial needs, promotes professional preparation and academic preparation. Of course, there are challenges. Scaling the approach is certainly a challenge, especially in sections with large number of students, 50 to 100 students. There's an entire section in the paper dedicated to some sort of rough calculations on how you might adapt the approach to large sections. There are some other challenges as well, which are mentioned in the paper. Concluding, the idea presented here, the approach presented here is based on the idea that we should teach programming languages to students in a mode that meshes well and leverages both how students think languages, not concepts. They put languages before concepts, and how they learn languages and new technologies on their own, online fora, YouTube video, Stack Overflow, and things like that. I hope, my goal with this presentation and this paper is that get the discussion going, challenge the idea how we teach programming languages. I hope it encouraged people to think, folks to think differently and to bring this back to their institutions. I encourage you to explore our web pages, especially our GitHub site, which involves all the language synopses, YouTube videos, presentations, and then some of the projects are posted as well. At this point, I'd like to thank you for your attention, and I certainly welcome you to contact me with questions and comments. Thank you.
Thanks, Saverio. I'm afraid that Saverio is not available for live Q&A, so that ends this session. Please do let me or Shriram know what you think of this scheme. Bye.